Good evening. It's good to see everybody tonight. Thank you so much for coming out to the 19th annual Nanotechnology and Engineering Symposium held here at North Penn High School. I am so excited to share with you the work that we have over 30 students and 11 research teams have taken a look at the challenges, these global challenges of energy, environment, healthcare, and looking at ways to solve these global issues using cutting-edge, new, different ways to solve these problems. So I'm really excited to share with that this evening. Now, before we begin, I do want to take just a minute or two to bring you up to speed a little bit about North Penn High School, the Engineering Academy, and how we got to do what we do here at North Penn, and more importantly, what your students and these students do here at North Penn. So the Technology, Engineering, and Computer Science department is broken up into several different course options that we offer to our students. And so starting way back in the early days, back when I started teaching here and even before that, we just had what we called industrial arts. That has spun off into technology education and has turned into technology and engineering education. And so if you look at our courses on the right-hand side, those are our technology and engineering education courses that you will see. Down below, we have some minor options, and off to the left is our Engineering Academy. And we offer many different course sequences as well as computer science program courses at the bottom of that. Now, the Engineering Academy here at North Penn started in 1999. At that point, I was in my 4th or 5th year teaching, and I was working with our department chair. And our former principal, Dr. Vincent Cotter, had asked the school, how do we create smaller learning communities here at North Penn? And with such a large school, we have a lot of students who are graduating from engineering. We thought in our department, why not start something called an Engineering Academy? And a long story short, my department chair and I traveled up to New York and we saw a program called Project Lead the Way. And we fell in love with it. We thought, wow, what a great opportunity for students to learn about engineering before they actually step out of high school. A chance to see a glimpse of applying these crazy math and science principles that they're learning in their classes and take it to the next level. So one of the things in the Engineering Academy now that these students have gone into is the senior capstone course. So that Engineering Academy course sequence is turned into an application process. So they now can take a look at what is mechanical engineering and civil engineering and all the different fields, and now in their senior year can actually apply it. So the senior capstone course that you're going to see these students present in is called Engineering, Design, and Development. And in EDD, the model nationally is where students take a problem and apply real-world concepts and solutions to develop some type of application and solution to the problem. We take it a little bit different here at North Penn. We like to do things above and beyond and give different opportunities, but it just didn't come naturally, and I'll explain just to give you a little bit of background. In this spring of 2003, I got an email from Drexel University, and it went out to all science and technology teachers saying, would you be interested in learning about engineering at Drexel University and bring it back to your students? And I thought, wow, what a great opportunity. Our Engineering Academy is still new at the time. We were like only about 3 or 4 years in, and that would be such a fun opportunity to learn about it and bring it back. So I signed up. And when I signed up, I was connected with their professor, Dr. Frank Coe at Drexel, who is now at University of British Columbia. And he said, hey, Mike, I'm in China right now giving a presentation. However, check out this research paper on our first project we're going to do when I get back. And I went, and my eyes got real big. And I looked at it and I said, I don't know what those words mean. And I said to my wife, I'm like, honey, I said, I don't know if I can do this. I thought I was going to do electrical engineering, and now I'm doing nanotechnology and materials. What does that mean? And my wife looked at me and she's like, Mike, what would your students tell you if you showed them something new and cutting edge and they said the same thing? And I'm like, well, you're right. And so I realized that, okay, I'm going to jump into this, scared to death. And when I got there, I fell in love with research. I learned about the nanotechnology and all kinds of different things, learned about material science. And I'm thinking, wow, so we can apply forces to materials. And forces, like you used to think of just mechanical force. You press a button or you kick something, right? But no, we can apply light as a force. We get a sunburn, right? So the light has energy. Or we talk about magnetism as a force. There's so many different energies around us that can do so many things. So we started looking at, well, how do we apply forces to materials to change their properties to make them useful? Hence the idea of what material science is. So introducing your students and these students here to what material science is gives them the opportunity to start thinking about their engineering skills and applying them to real-world problems. But then we took a next level. This isn't taught anywhere but here at North Penn, looking at the opportunity of nanotechnology incorporating into this. And so now how do we work at the nanoscale? We're talking 1 × 10⁹ meters, a billionth of a meter. Take a hair off your head, that's 80,000 nanometers. And these guys are working with things that are 100 nanometers, 200 nanometers, which is absolutely amazing. And it's really exciting to get them working in these different directions. So now we have to functionalize these materials. How do we do that? So we work with applying material science principles to different processes, and we do something called electrospinning. When I was at Drexel, I learned about electrospinning as a process of making super thin fabric, textiles, like your shirt, right? But these textiles can be functionalized. The fibers are smaller than the wavelength of light. You can't see them with your naked eye. We need special equipment, and these students will show you tonight what equipment they use. But we electrospin them. We apply high voltage power source, about up to 30,000 volts. Sounds like a lot, but the current, the amount of electrons is really low, so your cell phone has more power than this power supply, believe it or not. But we'll talk about that in the gym. But we actually produce these polymer nanofibers for various applications. They work with various different polymer solutions. You'll hear a lot of acronyms like PEO, PMMA, PCL, PVP, all of these different polymers that they're going to be working with tonight. And they'll learn how to prepare them using a polymer preparation process. And once these polymers are prepared, they actually then apply a force, a high voltage, right, electrical force, to a material to change its properties. And they turn this liquid into fibers. And these fibers look like threads, common hairs, but they can functionalize them so that way now these fibers, when you shine light on them, change color. Or when you apply a pressure to it, generate electricity. How's that possible? And these students are doing that. So wait till you see that tonight in their process. So we can make air filters, water filters. We can talk about different sensors and energy harvesting. Why not take the rain that hits our roof and convert it into electricity? Because every raindrop has a force. It's not one raindrop, it's millions of raindrops in one storm. That's wasted energy, turns into noise. Why not convert it into electrical? Feed the power grid back. Why not? Start thinking outside the box a little. It's kind of neat. And so these students will talk about those opportunities tonight. How do we see it at the nanoscale? We use an electron microscope. So here you can see a couple of our students actually measuring these fibers. And so if you look on the bottom right, those are nanofibers. One of those fibers is smaller than the wavelength of light. You can't even see it with the naked eye. When there's millions of them in front of you, you can. But by themselves individually, you can't. So we have to use a high-power microscope. And Hitachi High-Tech America has been working with us for years, and we're very blessed to be a part of a program that they have for us to use that. However, we look like we might be not in their program because they have to shift it around to different schools. But we've had this SEM here for 4 years, and we're looking at a way to bring it back into the fold. So we'll talk more about that later on this evening as well. And so here you can see some more images that were student images that were taken up here on stage of various different applications and materials that we'll get into. All of what we do here is not possible with the help of so many different organizations. The North Penn Educational Foundation has been our cornerstone, our rock since my first year teaching. I still have materials that in my lab that I got with one of my first years, like back in 1998, my second year teaching. I was able to use some equipment in a grant, and now all the work that we do is helped paid for with the research and the funding from the North Penn Educational Foundation. So it's really, really important that we can help support them as well. We also have support from our North Penn Curriculum Department as well to give us some high-tech equipment. You're going to see a stereo microscope down there, and that stereo microscope is going to give great vision to macro-scale materials. In the lab, you'll see, and also a Rheosense viscometer for measuring the viscosity of our polymers. So how do we get to this? In 2005, the first year we ran the Futures N.E.A.R program, I designed it and just started applying for different grants, and all of a sudden, in 2005, the N.E.A.R program was born. We were looking at how do we make this happen? And so it came from different organizations, and you can see all the companies that I've written for grants for that have supported us. And over the years, we've raised over $100,000, which has given us our vision. And we've gone from what is electrospinning and material science and nanotechnology to how do we harvest energy from wind, air? How do we improve the human condition by saving lives and reducing impact from injuries? Or how do we prevent concussions or replace damaged nerves? You're going to see a lot of that this evening, so it's really exciting. So without further ado, I'd like to hand it off to our teams. And you can see up here the 11 teams. Each team has their own name to give them a little bit of an identity to the research. So you'll hear them identified by that this evening. And so without further ado, I'd like to hand it off to our first team, N.E.A.R. Thank you very much.
Thank you for welcoming us to the stage. My name is Zach Dold.
I'm Caleb DeLange.
I'm Alex Burns.
And I'm Owen Fritz.
And together we are N.E.A.R. In our modern society, technology is constantly evolving. That new technology needs a way to supply it with energy. Only 13% of all energy generated is renewable. How can we maximize that? Our solution was to combine multiple methods of renewable energy into one material. What materials did we use? We used thermoelectric materials and piezoelectric materials.
In 1821, Thomas Seebeck invented a device that could find the thermoelectricity of a material. The Seebeck effect, as we now know it today, explains how thermoelectric materials create a current from a difference in temperature between two sides of the material. Today, we see this in everyday appliances like fridges, coolers, and thermometers.
In 1880, Pierre Curie developed a machine that relied on weight being added to a piece of quartz which would stretch or compress, creating an electrical current from the mechanical energy, creating piezoelectricity.
The first material we researched regarding thermoelectricity is called bismuth telluride. We found that it was one of the more efficient thermoelectric materials that we could get our hands on. Due to hazards regarding the material, we had to prepare the polymer and electrospin it under a fume hood to ensure safety for everybody.
After we created our material, we realized that testing it was not going to be as easy as we thought. There is no standard method for testing thermoelectricity, so we had to come up with our own circuit. This circuit consisted of a microcontroller that applies and records a temperature across our material. This data, along with voltage over time, aided us in calculating our Seebeck coefficient. Over 2 trials, we recorded an average Seebeck coefficient of 7 microvolts per Kelvin. There was a strong correlation between our temperature difference and our voltage created. This yielded a 74% efficiency. Our results were almost exactly what we were hoping for.
For our piezoelectric material, we used PVDF, or polyvinylene fluoride. We used it due to its large amount of pre-existing research, ease of use, and relative efficiency for what we wanted.
To test our PVDF, we use a similar but slightly different method. We utilize an analog discovery 2 device to record the voltage over time. Alex periodically tapped our material, and we recorded an average peak voltage of 200 millivolts on our best trial.
After testing PVDF, we then combined it with our thermoelectric material, bismuth telluride. Although we were able to generate a voltage from that material, we cannot test them and characterize them together. We then had to isolate both materials once again for performance testing, which then defeated the purpose of our research.
While trying to come up with a new way to test these combined fibers, we had a new idea. What if we mixed the bismuth telluride and the PVDF into paint? We started with PVDF, we mixed it together with a paint sample, we painted it on a piece of aluminum foil and tested it. The PVDF alone had a very similar efficiency to the fibers. We then made another paint sample mixing PVDF and bismuth telluride. After painting it again, our results were very successful due to the fact that we were able to measure both thermo and piezo at the exact same time.
This could be applied as a clear coat to things like windows or as a paint to homes, cars, and buildings, increasing the efficiency or generating electricity for those things.
And if we had more time, we'd like to then implement a third energy harvesting device, photovoltaics, or otherwise known as solar energy. We'd also like to then test on a larger scale basis to see how well voltage is affected by surface area. And last, we'd also like to see how we can store that energy in a battery or for later use.
Thank you so much for listening, and we would love to invite our next group up, N.E.A.R.
Thank you for joining us this evening. My name is Rakabal Hoke.
My name is Progjim Das, and together we are NRP.
The world's automobile industry is inefficient in garnering energy. Such inefficiency has propelled the use of gas-powered vehicles, which is harmful to the environment. Majority of the wasted energy comes from the cars being outside all day in the sun, but these can actually be gathered for later use.
So to solve this issue, we researched the study of photovoltaics. This is a field which is hugely inefficient in the modern world. To combat that issue, we researched Gretzel cells. But before that, let's dive into the topic of non-renewable resources.
Oil, coal, natural gas, and nuclear energy are the four main non-renewable sources of energy that we use every single day. These, however, are harmful to the environment as they pollute the air and contribute greatly to global warming and climate change.
However, the problem with non-renewable resources is that they're used by 64% of the world. Think about that, 64%. That is more than half the global population.
To combat this problem, we have a cleaner source of energy, which is the sun.
We plan on garnering the sun's energy through the use of solar panels. However, the problem with modern solar panels is that they are only 17 to 20% efficient. That means of the total energy that they collect, only 17 to 20% of that is actually outputted.
This is a dye-sensitized solar cell, or a Gretzel cell. It is a photovoltaic device that consists of 5 components, which are TCO glass, metal oxide thin film, dye molecules, electrolytes, and a counter electrode.
The great thing about Gretzel cells is that unlike typical solar panels, they are 50% efficient. That is a huge jump from what we had before.
One of the major components of the making of the Gretzel cell is anthocyanin. Anthocyanin are just fruits that can be used as sensitizers. The 3 fruits that we used were blueberries, raspberries, and blackberries. The first step is to crush the titanium dioxide into paste-like so it's easy to apply onto the TCO glass. Here you can see us crushing the anthocyanin into a liquid state because that's what we did for our specific experiment.
On this step, we are carefully placing the layer of TiO2 onto the anthocyanins. This is a very crucial step as we have to make sure that no spot of TiO2 is left behind. And on this step, to the left, you can see that the layer of TiO2 is being absorbed into the anthocyanins. Right after we take it out, we have to make sure that any spots of any bits and fragments of the anthocyanins are washed off with deionized water. And on the right, you can see the final results.
The final step is to slide down the TCO glass just a bit so there's a positive and negative end to attach alligator clips to find the voltage later on, securing it firmly with binder clips on each side. The main device that we used to characterize our Gretzel cell was the Keithley 2450. This device measures the voltage and current as well as the total power output as seen by the IV power curve. This is the general setup.
On the left, you can see a diagram of how our Gretzel cell works. What occurs is light passes through the TCO glass and right through the dye-coated titanium dioxide. As it passes through that, it coincides with the electrolytes. And on the right, you can see the final Gretzel cell that we created.
This is the data table of the 3 Gretzel cells that we made, consisting of raspberry, blueberry, and the blackberry Gretzel cell. Although the blueberry Gretzel cell had the highest voltage of 500, the raspberry Gretzel cell stayed consistent all throughout the 3 tests, so that was the most efficient.
Overall, we would say our research was a success. If we had more time, we would use other materials as our anthocyanins, such as strawberries. Something else that we would do is we would create solid-state solar cells. Because for our experiments, we crushed up the anthocyanins so that they would be in their liquid state. Something else that we would do is we would research other ways to garner energy, such as through the use of thin-film solar cells.
Thank you for listening. We would like to pass on to the gentleman of Espadacor.
Hello, I'm Braden Snow.
I'm Rowan Bernal.
And I'm Jackson Heyer.
And we are Spotacor.
Specifically, we're also here to talk to you about microplastic filtration.
More specifically, nanofiber alignment and how it pertains to mechanical filtration of microplastics. Let me throw out a couple values to start you here. 52 credit cards, 11 1/3 water bottles, or 4 1/2 rain ponchos. Sounds like a bunch of nonsense, doesn't it? Well, it isn't.
Each of those quantities is equal to the amount of plastic that you consume in microplastics every single year. And here's the real kicker. Over the course of your entire lifetime, you'll consume up to 2 large wheelie garbage bins worth of plastics. That's true for nearly everyone in the world. As you can imagine, this doesn't come without negative effects. Studies show that consuming this much microplastic increases rates of heart issues, aneurysms, and in some cases, even cancer.
And you might be asking, how do these plastics even get into our bloodstream? Well, unfortunately enough, our waterways are incredibly polluted. See, all of these plastics, they break down into the microplastics, and whenever you drink water, whenever you shower, whenever it even rains, those microplastics can get into your system, into your bloodstream, and cause all of those hazardous effects. And unfortunately,
The main problem is that wastewater plants are not required nor able to filter microplastics throughout their plants. Therefore, it's up to us as consumers to then buy filters to protect ourselves from microplastics.
see, the way that we can protect ourselves is through filtration. Filtration has 3 main things. You have the solution that you're filtering, you have the actual filter you're running the solution through, and you have the residue, which is whatever you have filtered out.
Our specific method of filtration used polycaprolactone filters, or PCL, in a vacuum filtration setup, which is where in the filtration space you create an air vacuum in order to pull the water sample from one end of the filter to the other in order to have more efficient filtration and faster filtration.
Now, to obtain microplastics, we use 2 different types of plastics as well as 2 different types of ways to create them. This way, we were able to have a large range of microplastics that would be able to go from all the way from 1 millimeter to 5 microns. As you can see in this picture, we were trying to get that range so we were able to show what's in your blood as well as could be caught in your mouth.
And in order to filter all of these out, we used 3 different filter apparatuses. First, we used wire spinning. Then we used drum spinning, and last, we used fork spinning. We'll talk about all these in depth, but first, let's talk about wire spinning.
Wire spinning was the most basic of our setups. Essentially, it involved hooking a wire mesh up to the copper collection plate of our electrospinning. There are a couple benefits that come with this. For instance, the wire mesh is conductive. It makes it a little bit easier to harvest the fires, and most beneficially, it sort of gives the microfibers a pseudo structure to adhere to, which helps with alignment. One of the qualities we were looking for in our filters was hydrophobicity, so they didn't break down in water. The cutoff for hydrophobicity was a 90-degree contact angle with a drop of water in the surface, and we found that our first filter, the wire spinning one, was in fact hydrophobic. In terms of our porosity, we were looking for stuff to be less porous so that less substrate is let from the one side of the filter to the other. Unfortunately, our first filter was found to be rather porous, which made it a little bit less efficient than the others. In terms of tensile strength, we found that our first filter had 186 psi worth of pressure that it was able to take before it snapped, which is quite staggering for the nanoscale that we're working on here. In terms of filter efficiency, we found that it had a 68.1% efficiency on how much microplastic it could remove from any given water sample, and you can see our final and initial weights of the filter up there.
And the next type of spinning we used was drum spinning. This involved taking wire and wrapping it around a rotating drum. The rotation of the drum allowed for the fibers to be stretched around the wire, adding for a greater alignment, which we can see affected our data later. And additionally, it had the same benefits as the wire spinning with the pseudo alignment and the greater conductivity. Unfortunately enough, these filters were not hydrophobic. And specifically for drum spinning, its porosity was even higher than the wire spinning before. However, to make up for it, it has a much higher tensile strength, being 267 psi, almost 100 more than the previously mentioned type of spinning. And in terms of filtration, we were able to get out 74.4% of the microplastics in the solution that we had running it through. You can see the initial and final weights. And the next type of spinning we used was
fork spinning. Fork spinning is a type of spinning that utilizes the bases of a very common type of spinning known as gap spinning, as well as drum spinning, as it has a rotating fork that contains the wires as well as 2 copper forks to create that conductivity and elongation and contraction of fibers that we're looking for to get a wide range of fiber sizes. Now, when looking at hydrophobicity, we weren't able to get it to be quite hydrophobic, but at the same time, it was hydrophobic enough that we didn't have to worry about it breaking down. When looking at porosity, we were able to get it to 26%, which was our best of the entirety of our tests, and turned out to be very effective. Now, looking at its tensile strength, although it wasn't the highest, it was still definitely enough that it would be able to withstand any type of water pressure in any type of household. When we finally looked at how our fork spinning filter worked out, we ended up coming up with 86.1% of our total plastics filtered through. As you can see in the water right there, there's still a little bit of particulate, but at the same time, it's much better than drinking all of them.
And when we start comparing the average tensile strength of all of the filters that we use, it is clear that drum spinning was the strongest. And unfortunately enough, the wire spinning fell almost 80 psi behind, while the fork spinning was just 20.
Following a similar theme in terms of filter efficiency, we found our wire efficiency was the lowest, with fork being the highest at 86.1%, with drum spinning not far behind. Quite frankly, for these level of filters that we're making, that's a staggering number to be removed.
Now, when we were wondering why, we really had to take a look much closer up, all the way down to 10 micrometers. And with this, we were able to see the total range that we really had of the sizes, and we think this is why we were able to catch so many more plastics. As you can see, we had up to 12 microns caught with the fork spun one, whereas the other two have very small fibers, and we're catching less overall because of the lower range.
And for future research, we want to start stacking these type of filters on top of each other to see if we could pull out even more microplastics than the staggering 86 number that we already had. What we would do differently is we would focus in on our research earlier in the year, so that way we could have run even more tests and gathered even more data to present. And the lesson we learned is really how to communicate our data effectively with each other so that we don't get upset and we can work together as a team. We are Spotticor, and we'd like to introduce Ecoplastics.
Hi, I'm Laura Pham.
And I'm Sophia Marcicano.
And we're Ecoplastics.
Have you ever thought to make a plastic out of an avocado? Neither do we, but we did it anyways.
And so today we'll be discussing our research in bioplastic development. Firstly, what is a bioplastic? A bioplastic is a plastic that contains organic material that degrades in the natural environment, or a plastic that satisfies both these conditions.
The bioplastics that Laura and I worked on, for the most part, contain a starch, plasticizer, acid, and deionized water. The starches we use specifically are carrageenan kappa, avocado powder, and tapioca starch. Carrageenan kappa not only acts as a starch, but as a plasticizer and binder. It's derived from red seaweed, which is a widely available resource. Avocado powder is something that Laura and I made. Using previous research, we determined that would be a good additive to another starch source. As for tapioca starch, it also had positive results in other research, so we decided to incorporate it in our other experiments. Now, after making our plastic solution, we needed a way to dry it, so due to limited resources, our two options were to let it air dry and use a food dehydrator.
Our first plastic, EPO1, was comprised of glycerin, the plasticizer, avocado powder, and carrageenan kappa, two starch sources that Sophia just described, deionized water, and UV dye, which we hoped would help us identify microplastics during the soil degradation testing. In outward appearance, EPO1 had a rough texture due to the avocado, yet it was still flexible. And that rough texture I just mentioned is especially evident in these SEM images.
For a second bioplastic, EPO2, it consisted of carrageenan kappa, acetic acid, which is commonly known as vinegar, glycerin, and deionized water. This plastic ended up looking a lot like a typical plastic you'd see. However, it was very brittle compared to EPO1. Now, seen in the SEM images, there's not much texturally to EPO2 besides the occasional air bubbles.
EPO3 was exactly the same as EPO2, except for the addition of avocado powder. The avocado powder added noticeable texture to EPO3 as it was much rougher than EPO2, yet it was also more flexible. And as you can see in these SEM images, the avocado powder is spread throughout the sample, which is especially noticeable in the cross-section.
Now, EPO5 was the most different from our previous plastics. It consisted of tapioca starch, citric acid, deionized water, and glycerin. This combination yielded a tacky, stretchy, and almost gummy-like plastic, and it was very easy to deform. In appearance, it resembled a lot like EPO2, with clumps of tapioca starch and occasional air bubbles.
And if you're wondering why we jumped from EPO3 to EPO5, don't worry, we can count. We just wanted to save the best for last. EPO4 and EPO6 contain the exact same components: glycerin, avocado powder, tapioca starch, deionized water, and citric acid. However, EPO6 had half the amount deionized water and slightly more tapioca starch. These adjustments did not change the resulting plastic anyhow, because both plastics were unfit for characterization. They both were not removed from the mold and didn't gel up during production like our last samples did. And as you can see in these SEM images, EPO4 was extremely flaky and paper thin, not ideal for a plastic.
Moving on to characterization, our first test was for heat resistance. So for this test, we used the Vernier Go Direct Melt Station to determine the melting point of our bioplastics. Now, all of our bioplastics achieved melting points of over 200 degrees Celsius. However, the highest was done by EPO1.
Our next method of characterization was tensile testing. We conducted tensile testing using the Mark 10 ESM 303 tensile tester, which is pictured here. Though tensile testing was difficult due to the slippery nature of our bioplastics, we used the data that we managed to collect to calculate the ultimate tensile strength and percent elongation of our plastics. As evidenced in this graph, you can see that the highest ultimate tensile strength was achieved by EPO2, followed by EPO2 dehydrated, and our lowest was achieved by EPO5 and EPO5 dehydrated. However, as you can see, though EPO5 wasn't our strongest, it was definitely our stretchiest, stretching up to 150% its initial length.
Now, our last test was soil degradation. So for this test, we used this wooden box here that we made here at North Penn High School. Now, as you can see on the graph, our bioplastics ended up gaining mass instead of losing mass. This was due to water absorption because our plastics were very porous.
Despite our plastics gaining mass, there was noticeable degradation in all of our samples, especially EPO2 and EPO3 dehydrated. From our experimentation, we learned that seaweed improves the tensile strength and texture of bioplastics, and that avocado pits and similar seeds are somewhat viable starch sources for bioplastic production. Furthermore, as evidenced by the noticeable degradation in EPO2 and EPO3, we learned that acetic acid aids in bioplastic degradation. If we had more time, we would continue our soil degradation testing and also experiment with alternate starch sources as well as alternate methods for curing and drying our bioplastics.
In conclusion, we determined that EPO2 had the best test results overall. Laura and I both hope that our research could help contribute to the future of bioplastic development. Thank you for your time. We'd like to hand it off to the next team, NitroFix.
Hello, and thank you for coming out tonight. We are NitroFix. My name is Claire Adams.
And my name is Caitlin Vaccaro.
27%. That is the current percentage of surface water that is contaminated with nitrogen. The nitrogen cycle is a repeating biogeochemical process which regulates the nitrogen in both living and non-living things, such as soil, water, plants, animals, and bacteria. The nitrogen cycle changes nitrogen throughout its various forms, such as fixed in the soil and non-fixed, which is gas. It's necessary for a happy and healthy environment. In the past 20 years, the agricultural farming industry has increased the need for nitrate-based fertilizers due to increasing population. This has increased the leaching nitrogen into nearby waterways, creating unsafe living environments for local wildlife.
So 3 ways to combat this excess nitrogen include candy carbon, which is sold by one manufacturer as a wastewater mix-in treatment, cover crops planted after cash crops to absorb all the excess nitrates in the soil, and bioreactors, big trenches filled with the carbon source, typically wood chips, for water to flow through. So our goal is to take this contaminated nitrogen water and turn it into clean, safe drinking water that won't harm any animals, plants, or humans. We chose to go with the wood chip bioreactor. This is because it showed the most efficiency in past research and it showed easy maintenance. There's an underground drainage system which allows the water to flow into a pit filled with a carbon source. The carbon source works because it contains bacteria that contains denitrifying organisms. This allows the nitrogen in the water to turn into nitrogen gas, and then it can flow out into the waterways.
We decided to create our own bioreactor, but with a twist. We used PVC piping as the main structure for our bioreactor. We then filled it with wood chips, but other carbon sources such as corn cobs were proved to be successful by other researchers. We then contaminated water with some nitrogen, and then we ran it through hoping to get cleaner, safer water.
So we used many different tools to characterize our experiments. This includes the spectrophotometer, a tool that measures the absorbance at different wavelengths of light. We used a turbidity measuring device to measure the cleanliness and clarity of the water, and a nitrate ion selective electrode to measure the nitrate concentration. This works because it has a membrane on the outside that only allows in nitrate ions. From there, an indicator electrode measures the amount of nitrate that just came in and compares it to a reference electrode.
On the bottom left, you can see an example of a bioreactor, which is about 60 feet long and 20 feet wide. Our bioreactor was about 2 feet tall and 6 inches wide, almost 30 times smaller than the example. Our bioreactor was also built vertically, where most are built horizontally. To run our tests, we contaminated 1,000 milliliters of water with 5 tablespoons of an everyday water-soluble nitrogen fertilizer.
So when we started our experiments, we filled the wood chip bioreactor with the wood chips, and then we went to characterize our contaminated water. We measured the nitrate concentration, the turbidity, pH, and the absorbance at all the different wavelengths. We started with 7.56 milligrams per liter of nitrate.
We ran the water through and collected it for testing again, and we found that the nitrate levels had actually increased when we predicted them to decrease. Their turbidity had also increased due to the extra wood chip particles in the water, and the pH remained about the same. We also used the spectrophotometer on this experiment, and we found that the only change was between the violet and green wavelength at about 400 to 500 nanometers. We did some online research and found that 220 nanometers was the ideal absorbance wavelength for nitrates, and our graph was fixed to 400 nanometers, so we could not accurately use this for our research.
We then filled the wood chip bioreactor up again with more fresh wood chips, and we ran deionized water through to see what would happen.
We collected the water again for more testing and found that the nitrate levels had increased again along with the turbidity and the pH remaining just about the same.
Finally, we took the wood chips, we put them in a bin, and we soaked them overnight in sink water to see if it would increase again.
After letting the wood chips soak for 24 hours and collecting again for more testing, we found that the nitrate levels had increased the most out of all of our other experiments. It is unclear where the extra nitrogen was coming from, since wood chips are not shown to contain any nitrogen.
So if we had more time, we would do research and experiment to figure out why the wood chips were causing the nitrate levels to increase. After that, we would find different carbon sources, such as corn cobs and all the compost that agricultural farms let out. We would also try different structural placements, such as completely horizontal and at different angles. Finally, we would increase the size of our bioreactor to make it more comparable to what agricultural farms would use.
Thank you, and we would like to hand it off to nanocarbon.
Okay, there we go. Hello, and thank you very much for coming out tonight. My name is Joseph Grasso.
And I'm Ryan Schellenberger.
And we are Nanocarbon. Together, we work to develop a safer and more cost-effective solution for removing carbon from the atmosphere. 410 million. That is the amount of people that could potentially be homeless due to the fact that the rising sea levels are being caused by the amount of carbon dioxide in the atmosphere, causing the polar ice caps to melt. In the 20th century, carbon emissions have skyrocketed. Unfortunately, in these past years, natural disasters have increased in intensity and irregularity. In 2023 alone, $380 billion were used into repair costs for everyone's homes.
To combat this problem, we researched three main solutions: electro, temperature, and pressure swing absorption. Electro swing absorption uses an electrical impulse to absorb and desorb CO2 at will, whereas temperature swing absorption uses a material that naturally absorbs CO2 and desorbs it when heated. And pressure swing absorption uses the increased chamber pressure to absorb CO2, and when the chamber pressure decreases, it desorbs the CO2. Amines are a commonly used but high cost method to run. Zeolites are a molecular sieve that filters CO2 with small pores and has an electrochemical pull on water and CO2 with high selectivity. And carbon nanotubes are an efficient but are efficient.
Our proposed solution is activated alumina. Activated alumina is a mesoporous form of aluminum oxide, basically meaning it has small intricate pores on its surface, allowing it to absorb various gases and liquids, most notably being water and carbon. This makes it a very viable solution for us.
Our experiment was broken down to 3 steps. First, we created a baseline of pure activated alumina by removing any impurities such as water and CO2 by heating it using a hot plate. Then we tested the CO2 absorption inside our gas chamber by flooding it with 16 grams CO2 by cartridge. Finally, regeneration, the process to unbind the captured CO2, was tested using the hot plate again. Throughout the experiment, the temperature of the hot plate was set at around 900 degrees Fahrenheit. Each step was tested for 10 minutes, and our data was collected using a gram scale.
The imagery above is an alumina bead loaded into the SEM. You can see the small crevices that were allowed the CO2 to get absorbed into the aluminum bead. This allows not only the CO2 to get absorbed, but the water molecules.
For our modification, we decided to create a solution of 14% aluminum powder, 16% PSS, and 70% deionized water by weight. We then electrospun this solution. PSS is a plastic that can withstand high temperatures of the regeneration of our alumina powder.
This data shows the CO2 percentage absorbed based off of our material's mass. Multiple experiments were ran, and the average percentage absorbed was about 5.7%. PSS, on the other hand, not only did not absorb CO2, but also lost mass throughout the experiment. If we had more time, we would like to improve the gas chamber with epoxy, filling any leakage that allows the CO2 to escape, possibly affecting our data. Another modification we would like to test out is with potassium hydroxide, which would improve the CO2 capture efficiency, and/or with sodium hydroxide, which would lower the regeneration temperature.
We would also like to dissolve our alumina powder in solution and find the optimal concentration of PSS for fiber generation in order to increase the amount of alumina available to the surface. In addition, we would like to electrospin with hydrophobic and hydrophilic material in order to decrease the amount of water absorbed in between steps. Thank you for your attention, and with that, we'd like to hand off our presentation to Cap Delight.
Thank you all for coming out tonight. My name is Nirvana.
And my name is Sean, and together we are Captolite.
For our research endeavor, we decided to look into the effects of light pollution and ways to reduce it.
This is what you could see every single night, given optimal weather conditions. However, what you see instead is a gloomy, moody mess without a single star in sight. The reason is due to an effect called sky glow, something that happens when light pollution is trapped within the atmosphere, unable to escape, brightening the night sky.
This is our Milky Way. A study from 2001 showed that about 66% of North American residents weren't able to see it from their own backyard. A more recent study conducted in 2016 showed that this measurement had actually increased to about 80%. If you didn't already know, it's 2024. Our technology has improved so much in such a short period of time that we don't understand the consequences that come along with it. Light pollution doesn't just affect stars, but our wildlife as well. Birds become disoriented and steer off migration course, and it disrupts their cycles. Hatchling turtles, they will tend to head inland instead of towards the sea because they are attracted by bright street lights, only be taken by predators or run over by vehicles. For humans, light pollution can cause a decrease in melatonin production, and this can lead to insomnia, and it has also been shown to increase risk of breast cancer. In 2001, a study showed that 40% of the US population couldn't adapt to the true darkness of the night sky. This is again due to sky glow.
Before the invention of the first light bulb, humans turned to fire as a source of light. However, as society advanced, so did our devices, leading Thomas Edison to the innovation of the first light bulb, an incandescent bulb with tungsten wire filament. However, due to its tendency to burn out within a year, we quickly switched to the fluorescent light, a glass tube filled with a low-pressure mixture of gases. And now we use LEDs, contrived of compound semiconductor materials.
So light pollution isn't caused by the light sources or bulbs themselves, but how we use them. Excessive amount of indoor lighting, having it released into the atmosphere through windows, or excessive amount of outdoor lighting, or street lights that aren't shielded properly. And our current solutions are either to use blackout curtains or warm tone lights rather than soft white, or turn off our lights completely. But these aren't the most feasible.
So what are we going to do about it? What comes next? We decided to look at polarized film. Polarized film is a polyvinyl alcohol sheet that is stretched and dyed with iodine during the manufacturing process. Some real-world applications of this are sunglasses, which protect your eyes from too bright or harmful light.
So we took a sheet of glass and applied our polarized film. We then created a pocket to hold our glass and our apparatus. We used a meter that reads lux, lumens, and temperature, but we'll mostly focus on lux. Lux is a measure of light density. And for reference, the average LED to light up a room has about 200 to 500 lux. We tested 3 different light sources, LED, incandescent, and fluorescent, due to these being the most common. We then created an apparatus to block out any external variables. We took a cardboard tube and cut a slit at the bottom for our lux meter to fit, and then a second slit in the middle to add our pocket and insert our glass. This was our apparatus completed, and we tested it through the 3 different light sources in 3 different environments: no glass, glass, and polarized film.
Here is our first graph with LED light through empty space without glass. As you can see, it has a pretty high measure of lux, but nothing too substantial. Adding in our glass, we can see that lux is reduced to a small amount, but again, nothing too substantial. Finally, throwing in our polarized film, we can see a very large reduction of lux from the rest of the measurements. Moving on to our incandescent bulb, keeping in mind that this is around 13,000 lux or above, we have our no glass measurement and our glass measurement. Keep in mind there is some variation due to the amount of time the bulb was on and the amount of time since its last test. Finally, throwing in our polarized film once again, we can see that lux reduced by more than half for the incandescent bulb. Lastly, our fluorescent bulb, again with no glass, glass, and our polarized film, reducing lux by quite a large margin in all 3 light bulbs. By combining all 3 of our graphs, we can see that by adding polarized film to windows, we can stop the amount of light by around 50% from escaping your homes and being trapped within the atmosphere.
So if we had more time, we would like to look into negatively photochromic dye. This is a dye that would fade upon contact with light and regain its color in the absence of light.
We would also like to integrate the polarized film on the interior of the glass. Doing so would help with wear and dispersion of light.
We also wanted to research transparent solar cells, and we would implement these on windows to allow any excess or wasted light energy to be reabsorbed and reused in our homes.
Thank you all for listening. We would now like to introduce our next research group, IRIS.
Good evening, ladies and gentlemen. I'm Tommy Moore.
I'm Adam Riley.
I'm John Steelhammer.
And
I'm Mason Stigler.
And we are Invisibility Research and Innovation Sciences, or IRIS for short. As many of you know, we celebrate Memorial Day this weekend, mourning the loss of those who gave the ultimate sacrifice in combat, while also being grateful for the ones who returned. We would like to ensure that more soldiers can return stateside by improving the current U.S. military camouflage, which is both inadequate and ill-suited for modern combat.
Camouflage can be simply defined as patterns and colors used to obscure the figure of its user. It's been used by animals for millions of years and only by humans in the recent history. It was first developed by the France in World War I, and since then it's been used in military applications worldwide. OCP, or Operational Camouflage Pattern, is the current camouflage pattern used by the United States military. When compared to other camouflage patterns, it performs very poorly, and there are better solutions. And they need 3 to 4 different camouflage patterns in order to be adequately adapted to different environments. It costs $5 billion taxpayer dollars to implement OCP when it was replacing its predecessor. We need a change, and the US military needs something to protect its soldiers in every environment possible.
To solve this issue, we propose an adaptive camouflage. This involves the ability to change color to match its environment. Adaptive camouflage would be able to have a uniform change from a dark forest green to a snowy white in an instant. Animals have been doing this for years, like chameleons. We have 2 ideas to make this possible. Our first idea is electrochromism. Electrochromism is the ability to change color due to an electrical force. On the right is an experiment we did with ITO glass and tungsten oxide, which Adam will talk about later. On the left is an experiment we did with turmeric and an electrolyte solution. Turmeric, as we all know, is a common kitchen spice. However, what you may not know is there's a chemical inside of it called curcumin, which allows it to be electrochromic. We made a solution with turmeric, ethanol, water, and food coloring, and soaked a paper towel with it and let it dry overnight. The next day, we came back and soaked it in our electrolyte solution, and while it was wet, we ran voltage through the paper towel and were able to change it from red to yellow, and by reversing the polarity, we were able to manipulate it back and forth until the paper towel dried.
For our next experiment, we tested tungsten oxide, a fairly commonly used electrochromic material. We began by making a solution comprised of deionized water, hydrogen peroxide, and ethanol, and then added tungsten nanoparticles to it. We then made a separate solution of polyethylene oxide, or PEO, and added deionized water to that. We then combined the two at a 3-to-1 ratio to make our final solution. We then began the electrospinning process. We mounted a glass slide of ITO glass, which is a conductive type of glass, to a collection plate, which can be seen here in this picture. We then electrospun and were left with a layer of tungsten and PEO nanofibers on the ITO glass slide, which can be seen. What can be seen in this SEM picture is those fibers on the glass slide. We then had to remove the PEO due to the fact that it would obscure the electrochromic reaction, and we did this by calcinating it, which is just heating it up. We then left with tungsten oxide particles covering the ITO glass slide, which can be seen in this SEM picture. We then began adding electrocurrent. On the left is the before picture. As you can see, it turns from a clear glass slide to the dark green color seen on the right. After this experiment, we realized that electrochromism is not the way to go for adaptive camouflage for 3 main reasons. 1, the reaction is very difficult to control. As you can see with our turmeric experiments, we were unable to get the paper towel to fully change color. Another reason is the chemical used are quite expensive and could not be used on the wide scale. Our third reason is the active power supply required for the electrochemical reaction to occur is just not feasible for any one person to use.
We believe that there's a better solution. Electronic ink, or e-ink, is used from a range of products from color-changing car paint to reading tablets. It has many advantages over electrochromism, including its fast refresh rate, which allows us to change images quickly and efficiently. It also provides a high resolution, which means we can accurately display the images. Its biggest upside is its power-saving consumption, and it uses next to no power, and we'll get back to that later.
Seen on the screen now is a single e-ink capsule. Now, the top part is visible and is currently displaying the positive white particles, which are separated from the black particles on the bottom by a thin layer of a nonpolar viscous liquid. These are then placed upon an electrode, which can hold an electric charge. Now, this system is stable in no voltage, meaning that it will not move in any way without an electric force. Now, when we have a positive electric field, the negative particles are brought down while the positive particles are pushed up. However, when we flip this, we see the opposite reaction, with the particles now passing by each other until the negative particles, which are now black, are now on top. This system is now once again stable with no voltage, requiring no power. Now, one of these systems works just like that. However, thousands of them work in tandem to bring us a complete image. Multicolored displays work, but instead of using two potentials, we now see 7 different potentials in order to gain fine control over each layer. These colors can then mix and match in order to create new colors.
With these e-paper displays, we are able to produce pictures with fine and precise definition. Along with the colored displays, the colors blend together easily. And of course, if we wanted to implement this into clothing, it would have to be flexible, so luckily they make flexible screens.
If we had more time, we'd like to develop this flexible e-ink technology into a textile format. We'd also like to develop a program that would directly create code to images directly from a picture.
We thank you all for listening. We'd also like to issue our thanks to all veterans in the world. Thank you so much, and we'd like to pass it off to our next group, Gyrostride Solutions.
Hello? All right. Good evening, everyone. My name is Simon Faraz.
I'm Ethan Spencer.
I'm Evan Spencer.
I'm Sean Kabir.
And we're Gyrostride Solutions. Ladies and gentlemen, close your eyes and imagine yourself walking across a thin beam. Now what happens? You're constantly shifting from left to right, fighting yourself to maintain your center of gravity, completely blind as to whether you're walking upright or about to fall over, right? This is what it feels like for an AOA2 patient to just walk normally. At all times, walking is a difficult task that consumes all of a person's concentration and then some. Whereas for most of us in this room, it comes second nature. This is what our research is based on: ataxia with oculomotor apraxia type 2, or AOA2, and how to combat its most fatal symptom, gait instability.
AOA2 affects 1 in 900,000 people. Take a look at the brain scans above. Did you see the atrophy in the back of the brain of the AOA2 patient? Well, this atrophy is caused by a mutation in the synataxin gene. And the specific region that this mutation affects is called the cerebellum, which is responsible for our motor function and stability.
One of the very likely effects of gait instability is falling, which is the second leading cause of unintentional injury-related death. So it's imperative that a solution be found to properly assist these patients and allow them to walk independently and freely. Current solutions do exist, but they tend to create problems alongside the ones that they fix. For example, the wheelchair. While it does allow patients to be mobile, their legs are not in use, so ultimately it can lead to muscle atrophy in the legs. It might also cause the patient to not be able to access certain facilities.
The scooter also has a similar problem. If someone is able to walk, then they have every right to do so. Being battery lift dependent isn't much more beneficial either.
Now the walker creates a unique problem. Notice how there's no back support. This means that it prevents backwards motion and creates the habit of leaning on the walker, which can lead to complications such as posture issues, as well as heel striking.
Personal assistance can cause complications as well because the patient requires the help or the time and effort of a second person who may not be available at times. In contrast, what we'd like to propose is what we call the halo walker.
Here's the concept design for it. Notice how it surrounds the user to make sure that they're protected on all sides 360 degrees. There is also a net attached to the walker at the top ring in order to make sure that if a person does fall within the walker, that they are suspended and they can bring themselves back up safely. Now, in a worst case, if they were to fall with the walker, a device we created called the self-stabilizing module located at the bottom of the walker will protect them by counterbalancing them. Luckily for us, similar principles are already implemented in pre-existing designs.
For example, the Segway. I'm sure many of you have seen this vehicle in use. The user simply tilts in the direction they want to travel, and using self-stabilization technology, the Segway will catch them and prevent them from falling. Similarly, this is a revolutionary electric bike that uses self-stabilization technology in cases of crashes to prevent injury. For our device, we needed to figure out how much a wheel and base system needs to work to stabilize itself from a tilted position. Using our acceleration data, we were able to find the angular position, velocity, and tangential velocity required to set the device upright.
We used the MPU 6050 chip to measure linear acceleration data and use aforementioned concepts, as well as DC motor circuits.
This is a visual representation of our stabilizing module. The red and green LEDs represent tilt in opposite directions.
Once we brought the tilt recognizing program into fruition, we began building the model. Here's what the final model looks like. Keep in mind the washers in the back of the device are there to keep the center of gravity at the center of the device, thus limiting additional variables to take into account.
Now, in order to test the efficacy of this self-stabilizing module, we ran a trial test, a total of 7 trials measuring the time as to how long it took for the self-stabilizing module to get back upright, as well as the highest degree of lean, which means the furthest tilt or angular deviation the object experienced before returning to our desired position. What we saw was that we observed the object oscillating back and forth until it reached back to its upright position. And the fastest time it took was 6.2 seconds. We also saw that we had a 71% success rate. Even though we had a good and successful run, we are not satisfied with the data, as a person shouldn't need more than 2 or 3 seconds in order to get back upright.
The failure of trials 2 and 5 show that improvements can still be made. For one, we'd like to create the physical model of our Halo Walker and test its strength to ensure safety of its users. Next, we'd like to make sure the device is capable of moving up and down stairs in case of emergency. And lastly, we'd like to create housing for the self-stabilization module. Nonetheless, we hope that further research is conducted so that AOA2 and other conditions that impair mobility can be a thing of the past.
Because balance is a right, not a privilege. Thank you everyone for listening, and please welcome onto the stage B&M Elevated Prosthetics.
Hello, I'm Samantha Blanchard.
And I'm Gabrielle Miller.
And we are B&M Elevated Prosthetics.
And today we're going to be talking to you about our research in prosthetic development.
Millions of people worldwide lose a limb in their lives. in the US alone, it's estimated that 1.7 million people use a prosthetic.
Of those people, over 66% complain of issues in relates to residual limb hyperhidrosis. Your body sweats to regulate internal temperature, and the excessive moisture gathered around the residual limb can cause irritation, pain, blisters, and a compromised grip.
Along with wearing a prosthetic leg, you also have to wear a liner to cushion and protect your residual limb. Unfortunately, most liners are made of silicone, which often traps in heat and moisture against the skin. So many doctors recommend using a moisture-wicking sock to help keep the area drier. Unfortunately, those aren't very effective and compromise the fit of the prosthetic. So there are also perforated liners out there to help, but they are not accessible to most people.
Our goal was to create a prosthetic liner with both cooling and absorption properties to help combat the negative effects of the residual limb hyperhidrosis. So here we have a heat sink. A heat sink is usually used in electronics, and it's a device placed to pull heat away from the surface, cooling it down, and keeping the entire system from overheating. Our goal is to apply a similar technology to our prosthetic liners, but at a nanofiber scale. We experimented with two polymers, polyethylene oxide, or PEO, and polycaprolactone, or PCL.
We electrospun both polymers using these same parameters to try and get the most accurate results possible. 7 kilovolts using a 19-gauge needle for 1 hour each. We then looked at them under the SEM to make sure we had a good quantity and quality spin. This is the PEO and PCL at 250 times magnification, and this is them at 600 times magnification.
So in order to test the effectiveness of our polymer, we created an artificial body temperature simulation. So on the bottom we have our artificial skin, which was a sheet of silicone, and then we have our heat source, which was a polyamide heat plate. We had a thermocouple underneath the polymer to record our surface temperature, and we had a thermocouple above the polymer to record the air temperature. And here's our setup of the heat plate attached to 4.5 volts.
Our first test was with our control, which had no polymer. Our average surface temperature was 123 degrees Fahrenheit, while our average air temperature was 95 degrees Fahrenheit. The next setup was using PEO, and the average surface temperature was 120 degrees, while the average air temperature was only 85 degrees Fahrenheit. And our final setup was with PCL, with an average air temperature of 90 degrees and an average surface temperature of 125 degrees Fahrenheit.
So overall, our PEO was on average 5 degrees cooler on the surface and 11 degrees cooler in the air. This, while it did not perform in the heat sink fashion that we anticipated, it was overall successful in keeping our entire system cool and would be applicable for our use. PCL, on the other hand, kept the surface at about 3 degrees warmer and the air temperature about 5 degrees cooler, meaning instead of pulling heat away from the surface, it trapped the heat inside like a blanket. The PEO could be applied to a wearable product if it was incorporated in fabric like a material, perforated material, and it would be worn much like another prosthetic liner or a sock.
If we had more time, we would take a deeper dive into desiccants and how we could combine them with our cooling material. We took a look at 4 common desiccants: rice, activated carbon, calcium chloride, and silica gel. And if we were to use them in application, we would take a powdered version of the desiccant and mix it with the polymer that performed the best in our cooling experiments. We actually were able to make a 5% PEO polymer with 7% rice additive before running out of time.
While we were never able to formally test this, in theory it would retain the same cooling properties that we proved earlier, while also being able to absorb some of the inevitable moisture inside of the prosthetic. Thank you for your time. We'd like to pass it off to CDX.
Good evening, ladies and gentlemen. My name is Anaf.
And I'm Rowan.
And we are CDX. Tonight, we would like to present to you our research on hydrogel synthesis.
And taking a deeper look into osteoarthritis and taking a deeper look into artificial cartilage as a potential solution to osteoarthritis.
22%. 22% of the U.S. population suffers from arthritis. If we're talking bigger numbers, that's about 54 million people in the U.S. alone.
This disease is characterized by the breaking down of the joints and underlying bone. This is a painful process and often leads to mobility issues later on.
Current treatments primarily focus on pain management and lifestyle adjustments rather than addressing the root of this condition. As the disease progresses, the damage to the joint and surrounding bone worsens, becoming increasingly painful.
So we thought, what if we could come up with a solution to replace the cartilage as it breaks down?
Our idea was to implement a hydrogel that could replace the cartilage as it is breaking down, composed of bacterial cellulose and polyvinyl alcohol.
This is bacterial cellulose. It is a nanostructure that is synthetically made by bacteria. Here's some of the bacterial cellulose that we dried out for analysis. And here's some of it under the SEM. Notice the top left image has, you're able to see the fiber structure at the top.
The second material we worked with was polyvinyl alcohol, or PVA, specifically one with a molecular weight of 145,000. We were going to use this material to help stiffen our bacterial cellulose for testing. We used the stereo microscope here to get a closer look at the crystalline structure of the PVA.
For our experimental procedure, it required us to make a 40% PVA to 60% water solution in order to set the bacterial cellulose in.
Due to size limitations, we had to cut our bacterial cellulose down to 7.62 centimeters long by 3.54 centimeters wide with a depth of 0.3 centimeters. And then, after we cut it down to size, we put it inside our pressurized chamber here. On the right, we have the main body and lid, and on the left, we have the various inner components. The two metal plates you see here are the top and bottom weighted plates that go on the top and bottom of this Teflon chamber here, which holds our bacterial cellulose and polyvinyl alcohol together. Here's a diagram of how we set up the chamber. We started first with a layer of polyvinyl alcohol on the bottom, followed by the bacterial cellulose in an L shape as seen here. As we started filling up the chamber with more and more PVA, we folded the top half of the bacterial cellulose down so it could fit inside the chamber. Afterwards, we sealed it up and put it into the oven.
And we were all ready to run until the oven we bought broke, which was a shame. But it's okay, because the science department lent us theirs. So we were underway. We put the chamber inside the oven, brought the oven out to the boiler room, closed it for 24 hours, and began our test. Once it was done, we pulled it out and let it cool for another 24 hours. While extracting, we were able to extract around a golf ball-sized-ish chunk of bacterial cellulose and PVA. After around 2 hours of constant chopping, we were able to extract our piece of bacterial cellulose inside the PVA. Here's the bacterial cellulose, and we split it in two for easier testing.
After separating the sample into two pieces, we put them into the oven for another 25 hours, 24 for drying and another hour of variable annealing. After the 25-hour oven period, we took them out and put it into phosphate buffered saline solution for another 24 hours before testing. Here it is inside the solution.
When we pulled it out of the solution, we did notice there was a slight issue. One of our pieces had a significant weak point that would later hinder our tests.
As can be seen here, the sample's weak point got caught in the top clamp of the tensile tester, which pulled it clean and had a clean break point along that weak point.
This was relatively okay because we were still able to get data, and for the force displacement graph, we got a force of around 120 newtons over a distance of 15 millimeters. And for the stress strain graph, we got around 0.9 megapascals of resistance over the same distance.
Here's the second sample we tested, which performed much better than the first. When we ran it through the tensile tester for the first time, we had an ultimate tensile strength of about 144 newtons before it slipped out of the clamps of the tensile tester. And if we translate that over to stress and strain, it's about 1.16 megapascals. Alongside the tensile testing, we also ran a compression test on our sample. And we found that our sample was able to withstand a force of 243.2 newtons when compressed to half of its original thickness, which is about 2.8 millimeters. When compressed further, we found that the measuring gauge we have here on the tester was maxed out and could measure no further without breaking the machine.
If we had more time and money, we would rerun our experiment with the knowledge we know now. We would reorient the bacteriocellulose in the chamber specifically, because that gave us a lot of trouble.
We would also run more practice tests with the chamber, as we had quite some difficulty working with it initially. And if we had access to better machines with less limitations, we would use those as the ones we have here in the high school were pushed to their limits testing our sample. Thank you everyone for your attention. We'd like to pass it on to our number one supporter, our door hinge, as we like to call him, Mr. Boyer.
I'm on the brown right now. You got perfect. Wow. So I'd like to bring up the team. This is the 30 students that I've had the most amazing year with. I just want to thank every one of these students for the excitement that they've brought every single day to the lab, the curiosity they had, and just the unbelievable questions that they would ask. And for me, what I loved about this experience is that every day I come to school, I learn. Right? So I'm not just a teacher, these are my colleagues on stage. We got the chance to grow together, to fail together, to learn together, to try again. And that's part of the learning process. And so for me, I feel absolutely blessed to be able to work with them every day and can't wait to see what their next endeavors bring for them as they are going to be graduating from here very shortly. So I would like to congratulate the seniors here in the Engineering Academy for all the hard work that you guys have done this year, and just want to say congratulations again. So thank you very much. At this time, we are in the process of getting ready now to walk down to the auxiliary gym where you can ask questions. They're going to have their demonstrations set up for you. You'll be able to see a lot of the equipment that we've used here in the lab live and up and running. If anybody would like to take any pictures before we go, we'll wait here for about another minute or two, and then we'll transition down to the auxiliary gym just down the hallway. Thank you again very much.